Screencast 18.11 Free Energy and Chemical Equilibrium. What can we say about the relationship between the two? Well, the big deal is that when you're at chemical equilibrium, you're not favoring products, you're not favoring reactants, you're not favoring melting or freezing, say, when you're at that state of equilibrium. You're right on the cusp, so it's not spontaneous in either direction, therefore delta G is zero. We can measure it this way by talking about the work function here. And when it's the same as the equilibrium constant, that's when you have equilibrium. So R is our gas constant, 8.314 joules per Kelvin mole. T has to be in Kelvin. And Q is that reaction quotient. Don't forget, when you're at equilibrium, they're the same. Q does equal the equilibrium constant. So let's switch over to that and just say in general state that the free energy will be zero when you account for that RT ln K, and when this is at Q is equal to that, that's when that's also zero. So we can now say that in general, the free energy change of a reaction at standard conditions is equal to the negative sign of the gas constant times the temperature in Kelvin times the natural log of the equilibrium constant K. That can be KSP, that can be K sub C, that can be K sub P. It's an equilibrium constant in general. So let's go ahead and calculate one. And we are decomposing water into its component elements, hydrogen and oxygen. I took the liberty of looking up some free energy changes under standard conditions in kilojoules per mole, and obviously for, as we've learned before, for pure elements in their most stable states, and those values are zero. And let's see if we can come up with the equilibrium constant K sub P. And, well, we got our values, right? So first we're going to figure out the free energy for the reaction, and then we'll plug into that being equal to negative RT ln K, natural log of K, and we'll have everything except K itself. So first we figure out the free energy for the reaction, and this looks like it's not particularly spontaneous. It's a positive value. And I wouldn't expect water to spontaneously decompose into hydrogen and oxygen. It is, after all, an endothermic process, and I guess it would be bad for our planet if all the water was in a process of decomposing into flammable hydrogen. Now we can plug into our delta G equals RT ln K because we got everything except K, right? Just watch out for your units. You've got kilojoules per mole here, but we've got joules per Kelvin mole for our gas constant, so that's what we want to standardize on. Convert that to joules by multiplying by 1,000. Convert this to Kelvin if we need to. Yep, 298. And looks like they just did it automatically. Interesting how they didn't add the 273 for you, but they converted on the fly, as they say. And then we solve for the natural log of the constant, and we get a negative 191 to the 0.5. And so if we take e to that value, that's how you remove that natural log. That might be something that you are not totally familiar with mathematically, but that's how it's done, giving us a ridiculously low number, essentially 0. Boy, is that a low number. And this is calculating the equilibrium constant using free energy. This is Screencast 18.11.